If you have already tried to throw something, you may have noticed that objects are flying into some weird direction and definitely not where you intended them to fly. Sometimes they fall to the ground, sometimes they can go into a completely crazy direction. We're gonna implement today the more intuitive throw, so all the objects will more or less go into the direction you were intending for them to fly. First of all, let's quickly discuss what we are trying to solve exactly. So we have an object, and with this blue arrow, I have pointed the direction we want it to fly to. Before the actual throw, we move the object along some amount of frames, and during all those frames, the object has some velocity. So that's the direction we are moving it with our hand before actually performing the throw, before releasing the grab trigger. And it represents the direction and the speed of the movement. Now let's see what's going on exactly before the throw. So we are moving our hand, it happens along several frames, and during those frames we move an object and then release it at some point. And at that point, due to some small movements of the hands just caused by the releasing the trigger or whatever reason, the vector can be significantly different from the one we were aiming for this throw. So when we'll release the trigger, the object may fly to this red direction, which is far from the blue one where we wanted it to fly. So what can we do to get closer to this blue direction? If you'll take a look at this picture, you can notice that it looks like some sort of average of all the velocities we had during several frames before. So we definitely can try to cache all those directions and then use them to calculate the averaged vector and use it as the real direction for this throw. And we're gonna do this both for the location change over those frames and for the rotation change. Alright, let's find our grab component. Our solution will be completely in this class, in this lecture. Here, first of all, you'll have to make sure that you have the event tick turned on for this class. You can check this in class defaults, and the start with tick enabled should be set to true. Let's set it to true in our case. Now event tick will fire. We're gonna need this to cache the vectors over time. Now let's create a few variables. We're gonna need an array for cached velocities and for cached angular differences of this grab component. First, we're going to use to determine the location difference, and second, we're going to use to determine the rotation difference over time. To determine the velocity during the current frame is pretty simple. You just have to take the difference with the last frame. So we will keep track of it. We will have a variable where we will cache the last position and the variable where we're going to cache the last forward vector. So we have created two variables for tracking the location differences. Let's now create two other variables for tracking the rotation differences, which we're gonna do using the forward vectors. Because we're gonna do tracking for two different things, let's create a sequence, and we start with our position difference. To detect the difference, we're gonna get the last frame location and just use a subtract to calculate the difference with our current world location. And this result, the result of this subtraction, we're gonna add to the array. Now, because we have already calculated the difference, we can set the current world location to this last frame variable. So it's gonna be used in the next frame. And because we cannot just add values to the array infinitely, we have to limit its size. So we're going to check whether the size exceeds some value, and if it is, we will just remove the oldest element, which gonna be just the element in index 0. This size you can try to determine using just trial and error. Just try different values and see which one works the best for you. And now we have to do the same for our rotations, roughly speaking. Let's get our forward vector, and again we're gonna have to see the differences between them, but this time we cannot just subtract. We're gonna have to find the rotation difference, And we can do this like this. So we're gonna have the quaternion, so the rotation that represents the difference between those two vectors. And following the same approach, we're gonna save it to a specific array. Here first we're gonna need to convert it to rotator, and then we can plug it to our vector array. And let's connect it to our sequence. Now let's update the last forward vector. And again, we're gonna have to limit this buffer size by just checking if it exceeds some value. And again, if it is, we just remove the element at index 0, which is gonna be the oldest one. I have decided to work with forward vectors, cache them to get the representation of the rotation, but you can try to use quads directly. So far, with this code, we're gonna have two buffers. Each of those will have 10 last location and rotation differences. Now, for the initial comparison, when there is a 0 frame, we're gonna have to set the initial values on begin play. So the first frame comparison will just give us 0, but it's better for it to give us 0 than some huge value for no reason. That's the location, and now the rotation represented by forward vector. Again, you can probably use just quads over here. I just decided to use vectors, a forward vector. Plug it in and connect it to our begin play. After all of this, we're gonna have two buffers with vectors stored inside them, and for both of them, we're gonna need to find the average one. So let's just create a simple helper function that we can use for this purpose. This function will take the array as an input. Then we're gonna iterate over this array, and we're gonna add each vector to some local variable. For the return, we will just return a single vector, not an array. So this is gonna be the average vector that we're gonna consider for our desired direction. Now here, let's grab this and use this variable. It's gonna be a local variable where we're gonna add continuously those elements. Let's now rename it. Now we can use it, and we're gonna get its old value, add the current element, and set the updated value to the same variable, so increase its for this vector stored in our array. And after that, we're gonna just divide this final huge vector for the size of the element, so maximum by 10. This is gonna give us the average vector. Now, where are we gonna call all of this? So let's find the try release, because we wanna throw on release, try simulate on drop, and set primitive comp physics. We can add our logic to this function. If you wish, you can try any other place. I will place the logic here for now, because in our case, we want to handle this throw in general if we are simulating physics at all. And we have this as an input of this function we can directly use to determine that. So that's exactly the moment where we kind of apply this throw in direction to the object, in case we have released it and we want the physics to be simulated for it. So we're gonna like correct this kind of moment by applying our pre-calculated vectors. So let's get the average using our function from both of those. Another benefit of this function, we already have here the primitive component that simulates the physics. And first we're gonna apply the impulse. We're gonna use it for the linear difference. But we will not apply it directly before, we will multiply it by some value. So this will give you control over the strength of the throw. Now just connect the result, and you will have to select the velocity change. Otherwise, it won't be exactly what we want to achieve. So we want our vector to be exactly the starting velocity for the throw. And for the rotation, we're going to use add torque in degrees. Here, I think we can just plug it in, and also don't forget to select the velocity change. And I've made one little mistake. Over here, we should switch the order. Otherwise, we're going to have the inverse direction of our throw. Now, let's test. Let's, for example, try to grab our pistol. Now we throw, and you see it flies somewhere where we potentially could have aimed. We can do the same with the boxes. Now we can try to play this kind of game. Intuitively trying to hit those boxes. This is my favorite. I actually missed. Let's try one more time. Yeah, now it's cool. Don't try it at home. And with all of this, now we have a more intuitive throw that can be used as a base for this kind of mechanics.